Good morning, myself Dr. A.N. Basugade, Professor and Head Department of Statistics, Gopal Krishna Gokhale College, Kolhapur. Today we are going to deal with testing of hypothesis 2 and that to a second part. In part 1 we have discussed about the small samples and that to a t-test. So the first test we have studied in previous part is testing of population mean. Second part is testing of equality of two means and pair t-test. Like that way t-test we have seen. Now we are going to deal with the chi-square test. So here again we are going to deal with the three tests. The first test is test of population variance, second is test of goodness of fit, and third is test of independence of two attributes. I will go with the first test as test of population variance, where the hypothesis H naught is such that sigma square equal to sigma naught square. One population is there whose mean is variance is unknown, so we have to test whether that variance is equal to sigma naught or not, so that we have to test. Now for testing this one, we will take a sample of size n, that is, let x1 x2 xn be a random sample of size n which is less than 30. It is a small sample drawn from a normal population with mean mu and variance sigma square. And we know that then these all the xi's are normal with mean mu and variance sigma square, and the sample variance is given by s square equal to 1 upon n summation xi minus x bar square, which is the sample variance. If it is sample mean square, then it is 1 upon n minus 1, same thing. Now we know certain results, that one result is ns square by sigma square is chi-square with n minus 1 degrees of freedom. Where this s is the sample variance, then it is ns square by sigma square. If this s square is the sample mean square, that is formula is 1 upon n minus 1 summation xi minus x bar square, then it is n minus 1 s square divided by sigma square has the chi-square distribution with n minus 1 degrees of freedom. Now here our hypothesis for testing is h naught such that sigma square equal to sigma naught square versus h1 such that sigma square not equal to sigma naught square. It may be greater or smaller also, we can write. Now as we know, ns square by sigma square is chi-square with n minus 1 degrees of freedom. Thus our test statistics becomes chi-square calculated is equal to ns square by sigma square, which has the chi-square distribution with n minus 1 degrees of freedom. Now under h naught, what is your h naught? H naught is sigma equal to sigma naught square. Okay, and therefore we replace sigma by sigma naught. So under h naught, chi-square calculated becomes ns square by sigma naught square is chi-square with n minus 1 degrees of freedom. So here the population mean is known, and therefore this is the test statistics. Now if alpha is the level of significance, and if chi-square calculated is greater than chi-square n minus 1 alpha by 2. Why it is alpha by 2? Because half is taken, not equal means two-tail test, and therefore we will take half region to the left side and half critical region to the right side, and therefore this or chi-square calculated is less than chi-square n minus 1 comma 1 minus alpha by 2. Then we reject h naught, otherwise we accept it at given level of significance. If h naught says that sigma square equal to sigma naught square versus h1 says that sigma square greater than, so one tail test, then we'll use the formula as if calculated value is greater than chi-square n minus 1 alpha, because full region is taken to the right hand side, then we reject the null hypothesis, otherwise we accept. If alternative is sigma square is less than sigma naught square, then we'll write it as chi-square calculated less than chi-square n minus 1 comma 1 minus alpha, then we reject the h naught, otherwise we accept it. Now case 2 is if mu is unknown Then test statistics is chi-square calculated equal to summation xi minus mu by square divided by sigma square follows a chi-square with n degrees of freedom. So under H naught, the chi-square test calculated becomes summation xi minus mu whole square divided by sigma naught square follows a chi-square with n degrees of freedom. If alpha is the level of significance, and as usual above whatever we have seen, so if it is two-tail test, two-tail alternative sigma square not equal to sigma naught square, then we'll take the chi-square calculated greater than chi-square n minus 1 comma alpha by 2, or chi-square calculated less than chi-square n minus 1 comma 1 minus alpha by 2 for rejection of H naught. Otherwise we accept it. If it is one-sided, in similarly we can accept or reject. Then the next one is the chi-square second test. So that will be the first test of testing the population variance. Now we'll go for the second chi-square test, which is chi-square test of testing goodness of fit. Goodness of fit means for a given frequency distribution, we can fit any distribution. You can fit a binomial, Poisson, normal, chi-square, T, like that way any distribution we can fit. But every distribution is not good for that particular data set, and therefore you have to test how to decide then which is the better one. So if you fit the distribution, then we have to go for the chi-square test of goodness of fit, whether that data is good for that particular distribution or not. That can be decided with the help of this chi-square test of goodness of fit. So here we can fit any distribution for a given frequency distribution, but it is not it may not be good fit for the given data set. For the given data set, whether the fitted distribution is suitable or not can be decided with the help of this chi-square test. Now what is our hypothesis for testing? H naught is such that fitted distribution is good for the given frequency distribution, and H1 such that fitted distribution is not good for the given frequency distribution. Now whatever distribution we have given, some xi values and frequencies are given, so those given frequencies are denoted by OI, that is called as the observed frequencies. And what we are expecting for fitting that particular distribution for binomial, what is expected frequency, so that we have to obtain as EI value. So let EI, OI and EI be the observed and expected frequencies. Here the assumptions are, what are the assumptions for this chi-square test? The sample observations are independent of each other. The second one, summation OI minus summation, so that is equal to summation EI, not square, it is EI, that is equal to N. That is the second, means total of observed frequency and total of expected frequency should be equal to N. Third one, none of the expected frequency is less than 5. So these are the three assumptions for this testing of goodness of fit. Under H naught, the test statistics is given as chi-square calculated is equal to double summation, not double summation, actually it is single with respect to I only. Single summation of OI minus EI whole square divided by EI has the chi-square distribution with n minus 1 degrees of freedom, or after simplifications we can get it as summation OI square divided by EI, that total minus n has the chi-square distribution with n degrees of freedom. So these are the two tests we have seen. Now the remaining test, the testing of independence of attribute, and the one more test of F test, so that we'll see in the next class. Thank you very much.